Hey everyone, and welcome back to the channel. Ever looked up at the night sky and wondered what's really out there? We see tiny specks of light, but those specks are entire worlds, each with its own story. Today, we're going on a grand tour of our cosmic neighborhood and beyond to figure out how scientists sort all these amazing planets. It's like being a celestial librarian organizing the biggest library in the universe. So grab your space helmet and let's dive into the fascinating ways we classify planets. First up, let's start close to home, right here in our own solar system. This is where the classic division begins. You've probably heard of this one. Terrestrial planets versus gas giants. It's the most fundamental way we categorize the planets orbiting our sun. Let's talk about the terrestrials first. Think small, dense, and rocky. These are the inner planets: Mercury, Venus, Earth, and Mars. They're called terrestrial because they have solid, rocky surfaces, much like our own Earth. Terra means Earth after all. You could theoretically stand on them, though you might not want to on most. Mercury is a scorched, airless world. Venus is a toxic greenhouse hellscape. Mars is a cold, dusty desert. And then there's Earth, our perfect little oasis. These planets are relatively small in size, but heavy for their volume because they remade of rock and metal. They have solid cores, mantles, and crusts. They also have fewer moons, or none at all, in the case of Mercury and Venus. Earth has one, and Mars has two tiny ones. Now, let's journey further out past the asteroid belt to meet the giants. Say hello to Jupiter and Saturn, the gas giants. These guys are colossal. Jupiter is so big that all the other planets in our solar system could fit inside it. Unlike the terrestrial planets, they don't have a solid surface to stand on. They are primarily composed of hydrogen and helium, the lightest elements in the universe, basically like giant superdense clouds. As you go deeper into a gas giant, the pressure and temperature increase dramatically, eventually squishing the gas into a liquid state, and perhaps even a solid core deep inside. We're still figuring that part out. They also spin incredibly fast and have powerful weather systems, like Jupiter's famous Great Red Spot, which is a storm bigger than Earth that has been raging for centuries. But wait, there are two more planets in our solar system, Uranus and Neptune. For a long time, they were just lumped in with the gas giants. But recently, scientists have given them their own special category, the ice giants. Why the change? Well, while they are big and lack solid surfaces like Jupiter and Saturn, their composition is quite different. Beyond the hydrogen and helium in their outer layers, they are made up of heavier elements, what astronomers call ESS. This doesn't just mean frozen water, but also frozen methane and ammonia. These ices are what give Uranus and Neptune their beautiful blue hues. Uranus is a pale cyan, and Neptune is a deep, rich azure. They are also incredibly cold, being so far from the sun. So, in our solar system, we have 4 terrestrial planets, 2 gas giants, and 2 ice giants. It's a neat and tidy way to organize our local family of worlds. But our solar system is just one of countless star systems in the Milky Way galaxy. The real fun begins when we start looking at planets outside our solar system, known as exoplanets. Since the first confirmed discovery of an exoplanet in the 1990s, we have found thousands of them, and the numbers are growing every day. And let me tell you, the universe is far more creative than we ever imagined. The neat terrestrial gas ice giant model doesn't quite cover everything we're finding out there. One of the most common types of exoplanets we VA discovered is something we don't have in our solar system at all, the Earth. As the name suggests, a super-Earth is a planet that is more massive than Earth but lighter than the ice giants, Uranus and Neptune. They can be anywhere from 2 to 10 times the mass of our planet. The big question about super-Earths is, what are they made of? Some could be rocky, like a scaled-up version of Earth, potentially with a thick atmosphere. These are prime candidates in the search for extraterrestrial life, especially if they orbit within their star's habitable zone, the Goldilocks region, where conditions might be just right for liquid water. Others could be more like mini Neptunes, with a small, rocky core surrounded by a massive, dense atmosphere of hydrogen and helium. These would be far less hospitable. Then we have the hot Jupiters. These are gas giants, similar in size or even larger than our own Jupiter, but they orbit incredibly close to their parent stars, often completing a full orbit in just a few days. Imagine a planet bigger than Jupiter, whipping around its star in less time than it takes for us to have a weekend. Because they're so close to their stellar furnaces, their surface temperatures are scorching hot, reaching thousands of degrees. They are tidally locked, meaning one side always faces the star, resulting in a permanently hot day side and a slightly cooler night side. These extreme conditions lead to some wild weather, like winds blowing at supersonic speeds and even rain made of molten iron or glass. They were actually some of the first exoplanets we discovered because their large size and close orbits make them easier to detect. Of course, the universe loves extremes. So if there are hot Jupiters, there must be cold Jupiters too, right? And there are. These are gas giants that orbit far from their stars, similar to our own Jupiter and Saturn. We also find warm Jupiters, which orbit at a distance comparable to our asteroid belt. The variety is just mind-boggling. But let's get even weirder. How about Chthonian planets? That sounds dramatic, and it is. A Chthonian planet is the leftover core of a gas giant that has strayed too close to its star. The star's intense heat and radiation literally boiled away the planet's thick atmosphere, leaving behind only the dense, rocky or metallic core. It's like a planetary ghost. We think some of the very hot, rocky super-Earths we've found might actually be Chthonian planets. And there are more theoretical types that we're still looking for. For example, carbon planets, also known as diamond planets. These would form in star systems rich in carbon instead of oxygen. Instead of silicate rock, their geology would be dominated by carbides and graphite. Under the immense pressure deep inside, the carbon could form a thick layer of diamond. Can you imagine a world with mountains of diamond? There are also ocean worlds, planets completely covered by a single global ocean, potentially hundreds of kilometers deep. Beneath the water could be a layer of exotic high-pressure ice, with a rocky core at the very center. Some moons in our own solar system, like Europa and Enceladus, are suspected to be ocean worlds. And we're finding exoplanet candidates that fit this description too. These are incredibly exciting places in the search for life, as where there's water, there's potential for biology. Finally, we have to talk about rogue planets. These are the ultimate cosmic nomads. They don't orbit a star at all. They were likely ejected from their original planetary systems during chaotic formation stages and now drift alone through the vast, cold darkness of interstellar space. It's estimated there could be billions or even trillions of these free-floating planets in our galaxy. Detecting them is incredibly difficult because they don't emit their own light. But astronomers are using clever techniques to find them. Life on a rogue planet sounds impossible. But some scientists speculate that a thick atmosphere or a geologically active core could keep a subsurface ocean warm. Enough for life to exist, even without a star. So, from the familiar rocky worlds and gas giants of our home system to the exotic super-Earths, hot Jupiters, and lonely rogue planets wandering the galaxy. The universe has an incredible planetary zoo. Classifying them helps us understand how they form, how they evolve, and ultimately where we might find another planet like Earth. The more we look, the more we realize that our solar system might be just one of many possible arrangements. What other crazy types of planets are waiting to be discovered? We're only just scratching the surface. Thanks so much for joining me on this cosmic journey today. If you enjoyed this exploration of planetary types, make sure to hit that like button and subscribe for more adventures into the universe. Let me know in the comments which type of planet you find the most fascinating. Until next time, keep looking up.